plan for today. Lots to do. I have a quiz for you on Standard 15, and then we're going to finish our discussion of Standard 16, and then we're going to jump into Standard 17. Chugging on along. Standard 17 focusing on optimization. I've got my usual office hours on Monday at 11 and at 1. As far as homework goes, there's going to be a homework 22, which I still need to actually post. That will be due on Wednesday. And on Monday, we will have a quiz over Standard 16 with the second derivative test. A little bit behind on grading retests. Some of you have taken retests in the last day or two. I haven't gotten those back yet. I've been trying to focus on grading near algebra exams the last couple of days. Quite the delight. But I'll get caught up on retest grading over the weekend. Any questions or comments before we get started for today? A statistics professor one day decides to distribute a 50-question true-false exam. That's not a bad idea. During the exam, the professor notices that one student sitting in the very back of the room is flipping a coin and writing down answers over and over. Flipping a coin, writing down an answer. Flipping a coin, writing down answers. This goes on for 2 full hours. Long after all the other students have left, that one student still flipping coins at the back of the class. Professor goes up to the student. Listen, she says, I know you aren't prepared for the exam. I know you've been flipping a coin to determine the answers, but what I can't figure out is what's taking you so long. Student glares at the professor and then says, shh, I'm checking my answers. And with that, it is quiz time. Flipping away. Go ahead and take a few seconds to finish up your thoughts. And pass your quizzes in, please. That's distressing. So congrats. Yeah, we could probably set something. No problem. Alrighty. So, last couple classes we focused on how do you find a formula, or how do you find local maxima and minima using f prime of x, using properties of the first derivative. And we sort of had this first derivative test, which I hope you used on your quiz to kind of help determine where functions can be increasing, decreasing, where you have local maxes or mins by seeing where does f prime go from positive to negative, or where does f prime go from negative to positive. And in standard 16, we're focusing, which we started talking about last class. We're focusing instead on how can we use properties of the second derivative, f double prime of x, if you will, in order to help us answer similar sorts of questions.
Do you finish your standard 16 packet? I didn't get one.
Oh, shoot, I didn't bring any extra state. They're posted on Canvas, or if you want, I can give you one after class.
Okay, great.
So, we said last time, we kind of talked about two different graphical properties that a function can have, where based on if f double prime is positive or negative. We said that if a function has a positive second derivative, if f double prime of x is greater than 0, we have a function that is concave up. And if f double prime of x is negative, we say that the function is concave down. Where the idea of a concave up function is you have a function where f prime of x, the slopes of the function, are becoming less negative and more positive as time goes on. Meaning as we go from left to right, f prime of x is getting more and more positive. And similarly, if f double prime of x is negative, that means f prime of x is decreasing, meaning we have a function that's sort of like this, where our slopes are becoming less and less positive and more negative as time goes on. So, Reagan, question for you. If we look at this concave up function I've drawn right here, looks like we have some sort of extremum at that point. What would you say that looks like? A local max or a min?
Local min.
Looks to me like a local min. And Katie, how about this function at kind of this point right here?
Local max.
It's like the location, the local maximum, I would say. And in fact, if you kind of take a look at this function we were looking at last class, where we sort of had some peaks and valleys, highs and lows, pick your friends, not your nose. We had two local maxes and a local min, and when we kind of divided up the different x regions of the graph into places where f double prime is positive versus where f double prime is negative, we said that kind of out to the far right, to the right of this dotted line I drew, f double prime of x was positive, and similarly to the left of this dotted line, we said f double prime of x, did I say positive? I meant negative. And in here is where f double prime of x is positive. I can tell the difference. I'm a math professor. So, if you notice, we sort of have this pattern where it seems to be where our function has local maxes, the function appears to be concave down, meaning f double prime is negative. But where a function is concave up, our one extremum in there is going to be a local minimum. And that is no coincidence, I assure you. So our next theorem, going to be on page 2 of the packet, is going to be the second derivative test. And what the second derivative test says is basically if you have a critical point where your function is concave up, then that critical point has to be a local minimum. And if you have a critical point where your function is concave down, then that critical point has to be a local maximum. So in other words, instead of using properties of f prime of x to help you classify do you have a max, a min, or neither, instead, second derivative test is going to tell us how can we do the same thing but using f double prime of x instead. So if f of x is a continuous function, then it's going to turn out to be the case that f of x has a local maximum at x equals a if f prime of a is equal to 0 and f double prime of a is less than 0. Sort of like this point here, where if f double prime is negative, meaning you have this sort of concave down, upside down bowl shape, and you look at this point right here, if you have a point where f prime is 0, meaning you have a horizontal tangent line, and your function's concave down, has to be a local maximum. Similarly, we're going to have a local minimum at x equals a if f prime of a is 0 and f double prime of a is positive. Like with this local minimum up here, where we have a horizontal tangent line, the curve flattens out, but it does so at a concave up point, meaning the function shaped like an upside down bowl. And so we say that that has to be the location of a local minimum. So if we have a local max where f prime of a is 0 and f double prime of a is negative, if we have a local minimum where f prime of a is 0 and f double prime of a is positive, what do you think we have if f prime of a is 0 and f double prime of a is also 0? Morgan?
It's unknown,
Why is that?
because the packet says so.
I've heard worse explanations than that. Unknown, because the packet says so. So what does that mean? It's unknown. Well, it turns out if your first and second derivatives are both equal to 0 at the point you're looking at, second derivative test ends up being kind of unhelpful. You could have a function like f of x equals x cubed, where this is going to be a function where f prime of 0 and f double prime of 0 are both 0. F prime is 3x squared, plug in 0, you get 0. F double prime is going to be 6x, which if you plug in 0 for x, you get 0. And this is a sort of function where you have neither a max nor a min at your critical point. And that was kind of, in fact, this is our example function of if f prime goes from positive to positive, then you don't have a max or a min. First derivative test says f prime has to go from plus to minus or minus to plus for that to happen. Here, we have an example of a function where both f prime and f double prime of 0 are both equal to 0, but we don't have a max or a min occurring. What would happen, do you think, if I tried to graph out f of x equals x to the 4th? Does anybody know what the shape of that graph looks like? Okay.
Is it just a skinnier parabola?
Yeah, it's in effect, it's a lot like a parabola, in that it's sort of this upward bowl shape. In fact, it's always concave up, because if we were to take f prime of x, we get 4x cubed. If we take f double prime, we get 12x squared, which is greater than 0, always. So we get a sort of parabola-like shape if we were to graph that out. This It's giving me a function where f prime of 0 is 0, 4x cubed is 0, that's equals 0. F double prime of 0 is also 0, because if you plugged in written equal to 0 always. Because if we plug 0 in for x into 12x squared, we would get 0 as an output. But, Anna, what type of critical point is going on here at x equals 0? Yeah, this would be the example of we have a local minimum going on. So in other words, if f prime and f double prime of a are both equal to 0, second derivative test isn't particularly helpful. You could have a local minimum. You could also have a local maximum. If I just took the negative, took f of x equals negative x to the fourth, that would be have a local max at x equals 0, because you just flip the function upside down. But you could also have neither. I would say if f prime and f double prime are both 0, then second derivative test just generally ends up being unhelpful. So SDT, I'm going to say, is unhelpful if either f prime of a equals 0 and f double prime of a is 0, or if f prime of a, let's see, does not exist. The reason being, if f prime of a does not exist, f double prime of a is also not going to exist. You can't have a second derivative without having a first derivative. And if f double prime of a and if f prime of a do not exist, that's the type of critical point where, well, this second derivative test isn't going to tell us anything. It's just generally unhelpful to use. Any questions or comments about what the second derivative test says before we look at a couple of examples? Alright, so let's look at a sample function. I'm going to look at the function f of x equals 2/3 x cubed minus 7x squared minus 16x plus 10. And just like in standard 15, we're going to be looking at functions now where we don't necessarily have a graph of the function in front of us. But I would still like to know, where does this function have local maxes and or local mins? So where do you think we should start? Gabe?
Find the first derivative.
Find the first derivative. All right. To do that, we'll get 6/3, so 2x squared minus 14x minus 16 plus 0. Neato Dorito. All right, Gabe, I found the first derivative. What do you want me to do with it?
So we can just go ahead and find a second derivative too.
You want to go ahead and find the second derivative?
Yeah.
Sure. Double prime of x is 4x minus 14. All right, we have found the second derivative. I think these will both be useful at various points in the problem. Where do we go from here? Charlie, any ideas?
We need to find our critical points.
Yeah, probably a good idea. Just like when we were using the first derivative test, it's probably a good idea to, pretty early on in the process, find the critical points. of f of x. All right, Charlie, so how do we find critical points? What did we talk about as kind of our process from standard 15?
Set f prime of x equal to 0.
Yeah, basically see where is f prime either 0 or undefined. In this case, f prime is a polynomial, so it's going to be defined everywhere. So our critical points are going to be where f prime of x equals 0, f prime of x does not exist. Just like it was in standard 15. So we're going to start by going through the same process. So if we do that, we'll get 2x squared minus 14x minus 16 is equal to 0. What should we do if we want to solve for x? Slash, can we solve this for x? Quiet mood today. Right.
Factor out of 2.
Factor out of 2. Sounds reasonable. I'll give us x squared minus 7x minus 8 is 0. James, what would you do next?
Then you need to factor that. So it would be x minus 8 and x plus 1.
Let's see, x squared minus 8x plus x will give us a minus 7x. And minus 8 times plus 1 is minus 8. I think it checks out. So if we end up with the expression 2 times x minus 8 times x plus 1 is equal to 0, what are the values of x that can make that happen? Nathan?
They are 8 and negative 1.
Yeah, we get either x has to be equal to 8 or x has to be equal to negative 1. And those are going to be our two critical points. And is that what you're going to say? Cool. So far, we've done the exact same process on this function that we would have done if we were using the first derivative test, if this was a standard 15 type problem. If this is standard 15 though, the next thing I think we would do is kind of draw out a number line, see what's f prime doing, is it positive or negative between each of our critical points, and use that to say if we have a local max, if f prime goes from plus to minus, or a local min if f prime goes from minus to plus at our critical point. With the second derivative test, though, we don't need to do that. Gabe had suggested early on that we find what f double prime of x is, so I think we can use that now. So how are we going to use, what should we do with f double prime of x and our two critical points? Charlie?
You can plug the critical points into f double prime of x.
Yeah, okay. So if we do that, we'll get f double prime of, Taylor, which one do you want to start with?
Negative 1.
Negative 1. Alright, f double prime of negative 1 is going to be 4 times negative 1 minus 14 is negative 4 minus 14, that's negative 18. And f double prime of 8 is going to be 4 times 8 minus 14, which is 32 minus 14, which is positive 18. I think that is coincidence that those are negatives of each other, by the way. I wasn't expecting that. Okay, so f double prime of negative 1 is negative 18. What does that tell us about what's going on at x equals negative 1? Morgan, what do you think?
At negative 1, we have a local max.
interesting. So you're saying we have a local max at x equals -1? Let's start with that one. Why do you say local max?
Because if f double prime of a is less than 0, then it's a local max.
Yeah, if f prime of a is 0, which does happen at both of our critical points, and if f double prime of a is negative, then the second derivative test tells us we have to have a local max. So we can say, I think, something like, since f prime of -1 equals 0, and f double prime of -1 is negative, I don't really care about the -18 number other than the fact that it's a negative number. We have a local max at x equals -1. And then, Emma, how about at x equals 8?
You have a local minimum because f prime of a equals 0 and is greater than, or it's, f double prime of a is greater than 0.
Yeah, we could say something similar. We could say since f prime of 8 is equal to 0, and f double prime of 8 is positive, we're going to have a local minimum at x equals 8. So what did we do? We started by doing the same process we would do for a first derivative test problem. We found our critical points by taking f prime, seeing where's f prime 0 or undefined. The critical points we got from that were at x equals, shop's crumbling on me. The critical points we got from that were at x equals 8 and x equals -1. So far the same as standard 15. The difference is, in standard 15, we then drew out a number line and saw how is f prime behaving on either side of our critical points. We would have had to check a point between -1 and 8, a point to the left of -1, a point to the right of 8. See, is f prime positive or negative there? And I think what we would have found is that f prime goes from positive to negative at x equals -1, which would have given us local max. And f prime would have gone from negative to positive at x equals 8, which would have gotten us a local min. But instead of doing that, we decided to use the second derivative test instead to kind of help us out along the way. And for the second derivative test, we just needed to plug in x equals 8 and x equals -1 into our f double prime of x. Since f double prime was negative at -1, that gave us a local max. Since f double prime was positive at x equals 8, that gave us a local minimum. Any excuse me. Any questions or comments? Let's do one more example. I'm going to skip the one at the bottom of this page and look at the top one on the next page. I will spare Lauren here and not right on the sideboard. Let's go through the same process, this time with a different polynomial. Next up, I want to look at g of x equals x to the 5th minus 5x to the 4th. And do the same process. See if we can use second derivative test to find local maxes and or mins. So this time, g prime of x is going to be 5x to the 4th minus 20x cubed. And g double prime of x is 20x cubed minus 60x squared. Nora, where do you think's a good first place to start working with these derivatives? Find the critical points. Groovy. How do we do that? Okay. Take the g prime of x and factor it out. Yeah. Same process that we did last time. We're going to start by finding our critical points. Where, just like last time, finding the critical points means we go with g prime of x, not g double prime yet, that comes later. So we'll get g prime of x is 5x to the 4th minus 20x cubed, which is 0. Nora, you suggested that we factor that? How would you go about factoring that?
Take out 5x cubed, and then I'll
5x cubed times
x minus 1.
x minus 4? Sounds reasonable to me. Let's see, 5x cubed times x is 5x to the 4th. 5x cubed times negative 4, negative 20x cubed. And if 5x cubed times x minus 4 is equal to 0, I think we're going to get 2 critical points again. Lauren, where is this expression going to be equal to 0?
X equals 4.
X equals 4. And? Where's that going to be 0? What would you have to plug in for x in order to make 5 times x cubed come out to 0? Yeah, x equals 0. So this time we're going to get 2 critical points, both of which are points where g prime of x comes out to 0. I want to start with looking at x equals 4. If we take g double prime of 4, we're going to get 20 times 4 cubed minus 60 times 4 squared. That looks scary, so I'm going to factor out a 4 squared and get 20 times 4 minus 60, which is going to be 4 squared times 80 minus 60. That's positive, that's positive. That's going to be positive. So, Carson, we found g prime of 4 is 0, g double prime of 4 is positive. What does that tell us about what our function's doing at x equals 4? What's that? Yeah, we have a local minimum because we have this condition occurring. So we can say that since g prime of 4 is 0 and g double prime of 4 is positive, g of x has a local minimum at x equals 0. By the second derivative test. If we take g double prime of 0, on the other hand, we're going to get, which 0 is our other critical point, we're going to get 20 times 0 cubed minus 60 times 0 squared, which is going to be 0 minus 0, glasses, equals 0. Franklin.
Wouldn't it be local minute x equals 4?
Yeah, that's what I said. Local minute x equals 4. Geez, Franklin, learn to read. Yeah, good catch. I don't know why I said x equals 0 there. So, what's going on at x equals 0 then? Lou? We don't know. Why's that?
Because f prime 0 is 0 and f double prime 0 is also 0.
Incorrect. G prime of 0 is 0 and G double prime of 0 is 0. Come on, F is the last option. But yeah, we're in this third state here, where we're in an unknown sort of state. We could be in a state like with x cubed, where we have neither a max or a min. We could be in a state like with x to the fourth, where we have a local minimum. We could be in a state like negative x to the fourth, where we would have a local maximum. We just can't tell, necessarily. The second derivative test fails. Since g prime of 0 equals 0, and g double prime of 0 equals 0, second derivative test fails to be helpful. So that's a bit of a bummer. So how do we tell what's going on at x equals 0? The second derivative test isn't telling us anything about whether we have a local max, a local min, or neither at x equals 0. How can we determine what's going on at x equals 0? James?
Go back to the first derivative test.
Oh, go back to the first derivative test? Okay. Second derivative test isn't telling us anything. Let's see what the first derivative test has to say on the matter. So let's use the first derivative test instead. So fortunately, some of our work's already done for us. We already know what our critical points are. We don't need to go back and relocate the critical points. So we can go right to drawing out the number line. And this will be g prime. We know g prime of 0 is 0, g prime of 4 is 0 from the work we did over here. Let's see. If we use this formula for g prime of x, Rotom, what's going on to the left of x equals 0? If I were to plug in a negative number for x, is g prime going to come out to something positive or negative?
Negative.
Let's see. We would get x cubed would be negative, x minus 4 would be negative.
Oh, so, then positive, sorry.
Negative times 5, I think it's actually going to come out to something positive. If we were to take g prime of, say, negative 1, we'll get 5 times negative is something positive. How about if we take g prime of, let's say, positive 1? John Henry? Would that give us something positive or negative if we plugged in a positive 1 for x into g prime?
Something negative.
Yeah, I think so, because we're going to get 5 times x cubed is going to be positive. X minus 4 is going to be negative, so that's going to give us a negative result. And then just for fun, if we were to take, say, g prime of 5, we'll get 5 times something positive for x cubed, and x minus 4 will be positive. So we'll get that. And so with that in mind, Aiden, what's going on at x equals 0 if we look at our number line? Are we going to have a local max, a local min, or neither?
Local max.
Local max, because g prime is going from positive to negative, right? Yeah. So we can say since g prime of x goes from positive to negative at x equals 0, I'm going to say g of x has a local max, it turns out, at x equals 0. And in case we wanted to verify what we said about what's going on at x equals 4, second derivative test told us that x equals 4, we have a local min. Well, g prime is going from negative to positive, so that's also, first derivative test would also tell us we have a local minimum at x equals 4. which is cool, but that's something we already knew from the second derivative test. What's going on at x equals 0 is of more interest to me because the second derivative test didn't tell us anything about what was going on there. So moral of the story is, sometimes if the second derivative test is unhelpful, like if you get one of these cases where your first and second derivatives are both 0, or if your first derivative is undefined, then you can just go and use the first derivative test instead. Because the first derivative test doesn't actually fail on you like that. Yeah, James?
So what are the advantages of the second derivative test over the first one?
Yeah, good question. Why might the second derivative test be useful to look at, or instead, if it doesn't always work? Katie, you look like you have something to say.
But I'm not quite sure. Doesn't it show also like the points for the second derivative? Wouldn't that be the point at which it turns like concave up and concave down?
It's true. We would have to go through some extra work. We'd have to set this equal to 0 and solve for x. Where we would get something like, say, x equals 0 or 20x minus 60 is 0, 20x equals 60, x equals a third. But we can certainly find where g of x changes from concave up to down or vice versa. These are called inflection points, by the way, we're going to see later on. James, I would say for right now, second derivative test doesn't really have any advantages over the first derivative test, other than the fact that it's maybe a little bit easier to work with sometimes.
Okay.
Because if you have your second derivative, you could, I would argue it's a little bit easier to just plug in your critical points into the second derivative and see, do we get something positive or negative, rather than kind of having to draw out the number line and see what's g prime doing on either side of all of our critical points.
Okay.
Personally, I actually prefer the second derivative test a little bit more because you just plug them into the critical points themselves and you don't have to check what's going on either side. But so from a ease of use standpoint, maybe second derivative test can be preferable.
Okay.
That being said, there is no circumstance in which the second derivative test would work, but the first derivative test would not. While there are lots of circumstances like this one where the second derivative test doesn't work, but the first derivative test does. So the first derivative test is never going to lead you astray. Second derivative test could possibly lead you astray and have you rely on the first one as backup. I thought it was nice. I thought I would show you both of these just so you could kind of see a sense of how does both the first and second derivative come into play for the purposes of finding maxes or mins. But and yes, on the standard 16 quiz, I'll probably say something like use the second derivative test to find where blah blah blah. But if you come across a function out in the wild and you want to know where does this thing have maxes or mins, you could typically use either test. And if you decide to use the second and it fails, then you just go back to the first derivative test.
Okay.
No, there's not a third derivative test. Well, that would be fun. By the way, if we're looking at like a height or a position or a distance function, we said if you take the first derivative of that, you get velocity. If you take the second derivative of that, you get acceleration. What do you get when you take the third derivative? Nora?
Jerk.
Wow, that's a rude thing to say to me. I believe you call me that. Aiden, do you have a more polite answer than Nora?
No.
Ouch. Yeah, you're both right. It's called jerk. So, like, you can think of the third derivative as sort of like a change in acceleration. So it's like if you're sitting in the car and you slam on the gas and you accelerate, you go from not accelerating much to a change. So where you're accelerating a lot really quickly, you kind of get like thrown back into your seat, right? Or maybe if you're in like a roller coaster or something, or the acceleration suddenly changes rapidly, it's like, oh my gosh, I'm getting jerked back. That is the actual term for the third derivative of your position function is called the jerk function. Not something we're really going to be dealing much with, but it's fun. It's a fun aside. Any questions or comments about the second derivative test? Yeah, Charlie?
What if you have a function that you take f double prime that you set a constant? Is that an area which?
Ooh, okay. Let's do an example of that. Actually, I think I gave you one like that on the previous page. So Charlie's asking, what happens if we take the first, if we have a function where f double prime just comes out to some constant value? So let's take a look at the function f of x equals negative x squared plus 6x minus 5. Well, we find our first derivative, we'll get negative 2x plus 6. We take our second derivative, we'll get a constant value, negative 2. If we find our critical points, you'll CP's. We'll take our f prime of x, set it equal to 0. And what would we get, Charlie, if we solve that for x?
3.
And we get negative 2x is negative 6. And we only get a single critical point at x equals 3. So what happens if we try and use the second derivative test on this? Well, if we plug in 3 into our second derivative function, Eden, what are we going to get if we take f double prime of 3?
Negative 2.
The same thing that we would get if we took f double prime of literally anything else. We would get negative 2. And Charlie, with that in mind, we have f prime of 3 is 0, f double prime of 3 is negative. What type of critical point do we got?
Local max.
Do we got? Gosh, I'm a professor. I need to use better language. Yeah, we're going to have a local maximum. So basically, if f double prime were to come out to some constant value, what that would just mean is that, well, first of all, it means that your original function is a parabola, ax squared plus bx plus c, because that's the only way to have f double prime just be a constant. But you would treat it the same way. You would find your critical points. We only got one. You would plug it into the constant function, and well, that would just literally come out to the constant. And based on if that constant is positive or negative, you could use that to tell if you have a max or a min. So nothing particularly special. If f double prime is constant, you would just treat it the same way. But keep in mind that finding f double prime, if your f double prime function is a constant, is, well, pretty easy. Good question, though. Are there questions or comments or concerns? All right. So, I have big news for you all. Our class has landed a contract with the Coca-Cola Corporation to design the next new Coke can. Y'all excited? Don't be too excited. Soda's not good for you. I drink too much of it as is. But get excited because it could mean we make lots of money. And that is going to lead us to standard 17. Where we're going to take what we've learned with first and second derivative tests, put it in practice with some word problems. So our goal is going to be to design the perfect Coke can. So whispering going on while I am talking about the perfect Coke can. My goodness. So what does it mean to have a perfect Coke can? Well, our goal is going to be to maximize the volume of the Coke can. Because what the Coca-Cola Corporation is going to do is trying to maximize how much Coke they can squeeze into each can, maximize the volume of the can, but we have two constraints. Coca-Cola Corporation is telling us we can't just do any shape that we want to maximize the volume. We can only use 6 pi square inches of material to construct the can. So we're given sort of this bound on how much material we can use to construct the can, because otherwise we could say, oh, construct a swimming pool the size of the universe. That would give us the maximum volume. Yeah, it would, but it's not very practical, so we have to put some constraints on this. We're only going to use 6 pi square inches of material to construct the can. And the other constraint we have is can has to be a cylinder. Why? Coca-Cola Corporation is proud to have cylindrical cans. And if they change that shape up, people would think they're getting tricked. By the way, did you hear the story about what happened when McDonald's at first started doing their quarter pounder burgers? Burger King thought that they could outdo McDonald's at their own game and make a lot of money by offering 1/3 pound burgers. They did not sell at all, or they sold very little, relatively speaking. Why? Because everybody thought that quarter pound burgers had more meat in them than the 1/3 pound burgers. People don't understand fractions. Anyways, here's the constraints that we're given. We have to make a cylindrical can. We're given an upper bound on how much material we can use to construct the can. So we probably want to use all of that, all 6 pi square inches of material. And we want to maximize our volume. Find a can that has the maximum possible volume subject to that constraint. All right, you all are my mathematicians. What do we do here? It's like I've given you a project and you have to figure out how you would solve this project. We've talked in the last couple standards, how do we maximize or how do we minimize something? But right now, we don't really have a function or anything to work with. Anna, what would you do first?
Find out what the volume of the cylinder is. The volume.
Okay, that's what I would do in step 2. Before I do any of that, first thing I would try and do in this circumstance I'm going to draw a picture. Help us visualize the process. Because oftentimes having a picture of what you're trying to do for these sorts of word problems can help out a lot with the old intuition of what's going on. Boom! We have a cylinder. And then step 2, and I'm going to take your suggestion, which is find formulas for the expressions that we care about here. So if we look at our cylindrical can here, look looking at this can, I would say that there's two different parameters that we can use for this can. That if we knew two certain parameters relating to the size of the can, that would be enough to tell us what the volume would be in terms of those two variables. So what two variables could we use to describe the size of the can here? Okay. Height and radius. Yeah, so I'm going to call the height h, I'm going to call the radius here r. Because r right now. Does anybody know how to find volume of the cylinder of radius r and height h? Aiden?
Is it pi r squared times height?
Pi r squared times height? James, is that what you're going to say?
Yeah.
Why pi r? Where did the pi r squared come from?
That's the area of a circle and you times it by the height and you get.
Yeah, so we could say that the volume here is going to be the area of the base multiplied by the height. Well, the height is going to be h. The area of the base, well, our base is a circle of radius r. How do you find the area of that? Pi r squared. So there's our volume, pi r squared times h. By the way, fun fact, if you go on to take Calc 2, you can use integrals to help you to prove the formula that the area of the circle is pi r squared. Fun fact. What are we going to do with that? We're going to wait until Monday, and we're going to see how can we maximize this when there's not one variable, but two variables in the expression we're trying to maximize here. So when we come back on Monday, we'll do a standard 16 quiz, and then continue our discussion of designing the perfect cookie. Hope you all have a good one. I'll see you all on Monday. Enjoy your weekend.
Thank you.